Okay, so I showed you that we wrote conservation of mass relation for the various of species. I don't like to use actually the term conservation mass. That's why I used, when I talked earlier, I said the balance equation for species I, because really species are not conserved, but you write the balance equation. Anyway, for momentum, this is actually conservation. What we do, we write a momentum equation for each species I, and then we sum them based on the amount of mass that they have. In other words, based on the yi. So what you will then get on the left-hand side is essentially mass times the bulk velocity acceleration, okay? In this term, the gradient of pi, when you sum over all the I, essentially you get a gradient p, where the p is essentially the sum of all pi. Pi is the pressure of species I in the bulk, so it's what we refer to as the partial pressure. And P being the sum of all the pi is a known law known as Dalton's law. So essentially, this is used here. In the viscous term, you're going to have a divergence of the sigma I, and the assumption is that the different sigma I form the sum of the separate viscous stresses form an overall stress for the mixture, which we refer to as sigma, and the mu here is going to be clearly something like mu I yi. In other words, it's the viscosity, the shear viscosity of the mixture, not of every species, right? Similarly, the bulk viscosity kappa, there are kappa I, and the summation will give you a kappa. So I don't pay too much attention for this because we're going to cancel it later. It's typically 0, and so we usually neglect it. But anyway, so mu and kappa are mass average viscosity coefficients. The last term is the body force Fi, and I left it this way because there are circumstances where different species, there are different body forces acting on them. For example, in a chemical mixture, you can have sometimes some ions or electrons that are conducting, and if you have an electric field, then only the electric body force on those species will be relevant. On other species, it's not. And so at the moment, I left it as such, but if, for example, the body force, the only body force is gravity, G, and clearly it acting on all the species the same way, then that term becomes rho times G because the sum of yi is 1, right? Okay, so what we wrote here essentially, building from a pure substance, is the momentum equation for the mixture, and it has the similar form as what we had for a pure substance. The next discussion will be on energy, and again we start with the total energy ET, and we write it for all the forces, all the work by all the forces, the body and the surface forces. And again, the sigma here is the stress of the mixture, right? And the Fi are the body force on species I, Vi the diffusion velocity, V is the bulk viscosity, the bulk velocity. Okay, and the rate of heat transfer is again, as before, is just written here. So from that total statement of total energy, I want to extract the kinetic energy, and I do that by taking the momentum equation, multiplying it vectorially by V, right? So that I have on the left-hand side, I produce rho d by dt of the kinetic energy. And then all the contribution here are subtracted from this equation, and what you end up with is an equation for the internal energy only, which is going to be very similar to the equation that we have for a pure substance, but we still have that term here. I'm leaving it just in case there are situations where body forces is acting on some species and not all, or they are acting differently on different species. Because you see, if again Fi was the same on all species, like let's say it was gravity, then G can be taken out of the sum, and the sum of Yi Vi is 0. And so that term is gone. Okay, so which is the comment made here actually. And perhaps the last minor comment I should make is that the phi, the dissipation function here, is of that same form as before, but the mu and the kappa here are for the bulk, right? It's the bulk viscosity coefficients or the mixture viscosity coefficients. Okay, so this is the energy equation written in terms of the internal energy. And of course, at some point, I will also rewrite that in terms of the enthalpy. Before doing this, I just want to make a summary of the conservation equation for a mixture. I know I've gone through this very quickly, but really one can spend a whole course only deriving this equation in a very fundamental way. Here the idea was to give you an idea of what they constitute, and that's why I focused a little more on a pure substance where things are clear, and I sort of try to generalize that. So what we have, the conservation of the total mass, then we have a balance equation for the different species, and as I already commented before, only n-1 of those are independent. Then I have the momentum equation of the whole mixture, an energy equation for the whole mixture, and in this equation we have quantities like the viscous stress, the dissipation function phi, which are known because we have assumed, I didn't say that explicitly, so let me say it now. We have assumed that every fluid is a Newtonian fluid, right? So each satisfy the relation between stress and strain, which was already implemented here. Needless to say that if this was not a chemically reacting system, then the main equation is the in other words, omega I is 0, and so we usually don't care for this species equation. They are secondary, they are not coupled. So the main equation are the mass, momentum, and energy, and these are the typical equation of gas dynamics, right? Of course, these are also known as the Navier-Stokes equation, the mass and momentum, and okay. So what we have left in this equation still to determine is what is the internal energy, right, E, and what is the pressure. In other words, how do they relate to other of the fundamental properties or quantities in this equation. So we need for this thermodynamics. We have to determine the heat flux vector Q. How does it generalize from just the Fourier law? Okay, there will be a generalization here, so we discuss. And we have to discuss also what are these diffusion velocity that I have introduced, which is related to transport. And finally, we have to define what are the rate of production destruction of species I, which is discussion of chemical kinetics. So you see why the complication in combustion is because really we have an interdisciplinary study that involves fluid motion, thermodynamic, transport, and chemical kinetics. Okay, before I go into this, I want to do something rather quickly because I will need it, but also it's a useful thing to know. Suppose that I want to write the conservation equation at an interface. So here is a part of an interface. It doesn't have to be flat, but the small segment of it is nearly flat. And I'm constructing a little control volume, this blue region. I can clearly write the conservation equation inside that volume, but my idea is to take the limit in which the volume shrinks to the surface. In other words, in which the volume shrinks to 0, and I'm going to get some interfacial condition. In other words, conditions that apply at the interface between either the same fluid or different fluids or different mixture and so on. Why is that important? Well, two things. One, sometimes the fluid dynamic equation allow you to have jump relations in the volume that you have, provided they satisfy appropriate relation. And we want to derive this relation. But second, this is useful in order sometimes to determine boundary condition. For example, if you have a fuel droplet of liquid and you want to determine what are the boundary conditions at the surface where it evaporates and burn or doesn't burn. The boundary condition will be determined by essentially these interfacial conditions. And so again, we are using Leibniz rule because what we want is to take the derivative of this volume, which, by the way, the interface may be moving in time, and so there may be changes in the volume. So what we want to take is the derivative of the time derivative of a quantity. Let's focus on mass conservation first. So the quantity is rho, the density. So d by dt of the mass inside that volume, right? So by Leibniz rule, it's written, or if you like, that's why I'm not using here well, it's essentially Leibniz rule that I earlier mentioned, right? But remember, I told you it doesn't have to be necessarily related. In other words, the volume, the control one, doesn't necessarily have to move at the fluid velocity. It can move at any velocity. That velocity here I refer to as VI, which is the interfacial velocity. So if I apply it to that volume, then I'm going to be able to write it as the volume contribution and the fluxes, if you want. So, this part, the rho dt, by mass conservation, I can replace by divergence of rho v. And this term, which is the surface integral well, this is just substituted here, right? So the next step is to use the divergence theorem and rewrite this volume integral as surface. You see, we are doing in some way the opposite of what we did before when we derived the equation. Before, we had this statement on, we wanted to express everything as the integral of a volume and then make a statement that since it's true for any volume, then the integrand is 0. Now I want to express the quantity as a surface. So I'm using the divergence theorem the opposite way. So here is the surface integral, which is equivalent to that divergence, right? Plus the fluxes due to the motion of the interface, VI. And now I can combine those two as two surface integrals into one, okay? And so the left-hand side, which is the time rate of change of the mass of this volume, is equal to this, okay, to this surface integral. Since this is what's written on top here, right? So far it's just a pure statement of mass conservation, which is I manipulated in this form. Now let's take the limit when the volume goes to 0. When the volume goes to 0, since the assumption is no mass is accumulated in that interface, then the volume V goes to 0, that term in the limit goes to 0. And what happened to this surface integral? Well, the surface has four boundaries, right? Four segments, two on the side that essentially go to 0, and then the one that I denoted here plus and the one minus here. So The remaining is going to be just the contribution from the upper surface and the lower surface, which is this one and that one, right? So it's rho plus V plus minus VI. The velocity of the interface is independent of whether it's above or below. But the normal, n plus and n minus, are always outward normals, so one is negative of the other. So if I call this one n, this is going to be minus n. So if I replace now the n plus with n and the n minus with minus n, what I have is the difference between these two, which is written here. But since the left-hand side is equal to 0, then this must be equal to 0. And that's the statement which tells you that the mass flux relative to the interface in is equal to the mass flux out of the interface, okay? And both are relative to the, of course, if the interface is not moving, all it tells you is mass flux in is equal to mass flux out. And we usually denote that by a jump, and I try to use this double bracket just for clarity. So that means the jump, the difference between one side to another. As long as it's equal to 0, it doesn't matter if I say which side is which, but once the right-hand side is not 0, we have to abide by some rule that says so. So we have to be consistent when we say the jump is which side minus which side, right? Okay, so this is about mass. We can write similar, and I'm going to rush through the next 2 or 3 slides. We can do the same exercise to the balance equation of species I. So the accumulation is going to be 0. We are going to have fluxes through the surface up and down. But now the fluxes are not only convective fluxes, but convective plus diffusive, because the total flux is convective and diffusive. And so the left-hand side is very similar to what I had in the previous relation. The right-hand side, however, there is the mass production or consumption of species I. Well, it depends if that surface is there is reaction on the surface or not. If there is no reaction, then clearly that term is 0 and we are done. But if there is a reaction, then there will be, this term will reduce to a surface rate, right? Which, because when the volume shrink to 0, then the distance shrink, become like a delta function. And so the contribution of the volume will be just the surface reaction rate. So in other words, it's the rate of production of species I per unit area along the surface, if it exists. It may be 0, so then it's 0, okay? So that's going to be the statement of that come out of the balance equation of the species. We can do a similar thing for momentum, and what you end up is the following statement. Remember that that's a vector equation, so what we are going to get is the jump of the 3 quantities in the 3 direction. And what you get is P dotted with a unit vector n, the momentum rho v times Vn minus Vi. Vi is the velocity of the interface, and the dot product of sigma by n. Okay? The jump in all this is equal to 0. Now, since it's a vector equation, we can... I didn't do anything to it yet, but I'll simplify it later. The third equation that the next equation we want to focus on is on energy, and I will leave it here as the total energy, okay, at the moment, and replace the total energy by energy plus kinetic energy, and then replace the internal energy with enthalpy. So the statement is, as you see, expressed here, just following the similar steps that I did before. I'm not going to discuss too much of that now, but I'm going to do, I think I have a simple example just to illustrate the idea soon. So here are the conservation, the jump relation that you will get, which involve mass, momentum, species I, and energy. written in the form of using the enthalpy and so on. So in fluid mechanics, and that's an important statement, discontinuities are allowed within the continuum framework, provided the variable across the surface of discontinuity are such that they satisfy the fundamental laws, which are expressed here in terms of jump relations. If they satisfy this, is acceptable. Okay, a simple version of this is known as the Rankine-Hugoniot relation. The Rankine-Hugoniot relation come up if you neglect viscosity, so this sigma is gone, right? And you focus on the mass and momentum equation. Well, the mass equation is written here. So this is essentially a simple statement that say the mass flux in is the mass flux out. The momentum equation, remember it's a vector quantity, can be split into two. Now sigma is 0, so we have only two terms here, Pn and rho v and so on. So if you dot it with n, so you get here n dot n, so you get the normal contribution of change in momentum across the interface. So you get P, so it's the P, plus here you're going to get rho v dot n, but which is this, rho v dot n times this, right, equal to 0. This is the normal contribution. It tells you that the pressure change is related to the normal momentum change in and out. And the last, the two other relation that you get is when you take the cross, you cross this equation with n. N cross n is 0, and this term will just give you, well, there will be two terms there. One of them is v cross n, and then you have rho v dot n minus vi. But rho v dot n minus vi from mass conservation is the same on the left as well as on the right, or on top and bottom, and so it factor out. And if it factor out, the only thing left is v cross n is 0. V cross n is the same thing as that, but it's a more accurate way to put it this way. Otherwise, if you just do v cross n, you're changing the orientation of the two tangential components. So the statement here is simply that the tangential component to the interface are conserved. In other words, they do not jump, okay? And writing it as I wrote here, then you're not changing, as I said, the orientation of the two tangential component. And the normal component tells you that the normal momentum change is related to the pressure. Of course, I have eliminated here the sigma, the contribution to the viscous effect. There are many fluid dynamic problems, for example, film. In film theory, then you have a film, the interfacial condition is related, there are shear forces on one side but not on the other, and the boundary condition that you develop on the interface is essentially obtained from this expression when you satisfy it on both sides of the interface. Okay, so, but of course when you do that, you have to also make some statement about if you have, for example, if you have surface forces, surface tension, it's something that you have to add here because it's not incorporated in that discussion. Okay, so I did not have the example that I thought in mind, but they will come up. The two examples that I was going to bring in is just the boundary condition that you introduce at the surface of the droplet when a droplet is evaporating and burning. So what are the boundary conditions that you introduce there? The boundary conditions simply come from that expression. Of course, in the droplet, the assumption is that there is no chemical reaction at the interface, so this is gone. And then if you use the diffusion law that I will introduce later today, this equation gives you the proper boundary condition. And I think when we talk about droplet and spray on Friday, I will show you that back. I will need the Rankine-Hugoniot relation in other contexts that we are going to discuss here. And so I wanted to spend a few minutes and discuss that before moving on. Okay, so we are now moving to thermodynamic and transport, which is needed in order to complete the discussion of the governing equation. So now, instead of a pure substance that we know that any property depends on two other thermodynamic property, we know that in a mixture it depends on n plus 1. N minus 1 species, because there are only n minus 1 independent, plus 2. So, yes?
This is Gibbs's phase rule.
It is?
Is this Gibbs's phase rule?
Yeah, okay. Basically, right. That's right. So so the assumption is that the n fluid are in equilibrium, and they are uniquely determined by the n minus 1 concentration, if you like, plus 2, right? So, for example, if all the species are ideal gases, then I can write for all the species that Pi is rho I RT divided by Wi. And if I sum over all I, after substituting for rho I, rho Yi, right, then rho RT pull outside. The assumption is that the temperature of all the species is the same, clearly. And then what you have here is the sum of Yi divided by Wi, which you may recall that this was exactly 1 over the molecular weight of the mixture. And so what I get here is essentially the ideal gas for the mixture, okay? We are going to run through all the thermodynamics quantity that I introduced before, talk about their relation now to the mixture. So, for example, this internal energy E of the mixture is going to be the mass-weighted internal energies of species I. So it's EI, YI, summing over all n. Same thing for H is the sum of YI, HI, summed over all n. And since each species is an ideal gas and it satisfies EI plus PI over rho I, then if you sum over all I and you use this relation, clearly you get that also the mixture satisfies this relation. So the relation between internal energy and enthalpy and pressure and density is given here for the mixture. Each of the species is an ideal gas, and therefore internal energy and enthalpy are a function of temperature only. And so one can write, as we did before, by integrating the definition of the CVI or introducing the definition of the specific heat, CVI and CPI, that EI is the reference EI plus the integral of CVI from the reference temperature to T, and the similar thing for CPI. So these EI naught and HI naught are essentially reference values, are the reference internal energy and enthalpy at the reference temperature T naught, okay? And that's the units, of course, joule per kilogram Kelvin. One can, just the top is a minor comment that I wanted to say, that usually the CPI, here, the CPI, well, they are all function of temperature, clearly, and very often one uses the dependence on temperature from some NASA files where they have expressed the dependence on temperature by a polynomial, and you can find those coefficients A1, A2, A3 for different species tabulated there. Of course, today it's probably computerized and everything is easy to get. But it's usually done in terms of the specific the specific heats express the molar heat capacity, the molar specific heats. And so it's not the small Cp or C that I have used, but I've used here a capital C to indicate that it's molar and not mass-based, okay? So the relation is, of course, that this is Wi Cpi, and so what is usually tabulated, it's the capital Cp divided by R, okay? Okay, so this was just a minor comment. In most of theoretical studies, we assume that Cp is constant, but we are going to do that later. The specific heat at constant pressure of the mixture is therefore can be defined as Cp being the sum of Cpi, in other words, mass weighted. And as a consequence, the enthalpy can be written, for example, as the sum of YIHI, that's the definition, and therefore can be written as the YI, the specific enthalpies, as we call them, the one which are the reference enthalpy, those we call the specific enthalpies, plus YI times the integral of Cpi dt. Now, if you consider this sum at fixed yi, then yi Cpi is Cp, and then that's just the integral of Cp of the mixture, okay? But this quantity is an important quantity because different species have different specific enthalpies, and the sum is of relevance, as we shall see. In fact, each species I, the reference enthalpy, is chosen as the heat of formation at some standard temperature T0, okay? Remember I said that we have to choose a common reference, and that's the definition. So for example, so I think it's repeated here. Here is the definition of the heat of formation. So Hi naught are chosen as the heat of formation, and here is the definition of the heat of formation. It's the heat that evolved or absorbed when 1 mole of substance is formed from its element in their standard state. And the standard state is the form that is the most stable at room temperature and atmospheric pressure. So for example, what is the heat of formation of water? So the heat of formation of water is going to be the heat the amount of heat taken out when you form water from the basic element, which is hydrogen and oxygen. These are the two which are stable at room temperature and atmospheric pressure. And so the amount is essentially 13.435 kilojoule per gram. It minus because it's the amount of heat taken out. By the way, if you look at tables, you will see sometimes this value, but sometimes a slightly higher value. And the difference is if you're talking about the heat of formation of water in a gas form or a liquid form, and the difference between the two must be the latent heat of vaporization, clearly. So here is a table taken from Glassman's book, and you see the 13.44 or the 15.84, and it's indicated if it's gas or liquid. And also you can see, okay, I wrote it here, I put it back in the next bullet. By definition, therefore, the heat of formation of all the elements which are in their standard state is clearly 0, right? Because of, right, by the definition here. So clearly the heat of formation of hydrogen, oxygen, nitrogen is all there, all 0, as you can see in the table here. But the heat of formation of oxygen atoms is not 0 because it's not in the stable state, clearly, and you have to break a molecule of oxygen to get O, and that's the amount of heat which is required. So, okay. Now, once we know the heat of formation of different element, we can define the heat of reaction. but that's a heat of reaction at a given temperature. Let's say at the reference temperature T naught. So for example, if we have methane plus oxygen give you CO2 and water, the heat of reaction of 1 mole of CH4 at room temperature is going to be now the bar on the H here, it's because it's per unit mole instead of per unit mass, just for consistency of notation. So we have 1 mole of CO2 that it's formed, 2 mole of water which is formed, minus 1 mole of CH4 consumed and 2 O2. Now O2 is 0, so it's gone. And you look at the tables clearly for the heat of formation of CO2, water, and CH4, and you add them up, and that gives you the heat of reaction of that reaction, okay, at the temperature T naught.
That's kilojoules per mole of what? Of the methane?
Of methane, yeah, because I'm using 1 mole of methane. Yeah, thank you. It should have been specified, but oh, you mean here?
No, that's
No, this is per unit mole of whatever, but what I meant here, it's usually my H was enthalpy was kilogram per unit volume per unit time, and here is mole per unit. Okay. Okay, so that's the heat of reaction at the reference temperature T naught. What about if I want to calculate at a different temperature? Well, at different temperature, then it's the heat of formation at the reference temperature plus the integral of the Cpi dt from that reference temperature to T. And if I know that functional dependence, clearly I can compute that at any temperature. Okay. Of course, in one of the other courses, you will go into more details into these things, I'm assuming, but I want to just briefly bring up those standard definitions. Okay, the next thing that I want to focus on, so what did we, we focused on the thermodynamic variable. So now the next thing that I want to focus on is on the transport, and the first thing is the heat flux vector. Now remember, for a pure substance, the only thing that we had that contribute to the heat flux was Fourier law of heat conduction. In other words, the heat flux was due to temperature difference. But now, if you think of a fluid parcel, then there is also a contribution by diffusion that can carry heat in or out of that volume. And that is described by the second term here in this vector Q. What you have here is rho I in principle, rho times yi, rho I, energy hi times vi. So it's the flux of the enthalpy, right? And you have to sum over all I because all the different species can diffuse in or out and therefore contribute in this transfer. And then you can also have some radiation flux, which I didn't mention before. Actually, it should have been also relevant to a pure substance. But I'm going to probably neglect that in the future and add it only when needed. So, but in general, you will have a contribution there as well. So if we go to our energy equation written in terms of the enthalpy, which if you remember have taken this form, all I have done here, I have changed the Q and substituted what the different contribution are, the Fourier heat conduction and the diffusion fluxes. Okay, so if we neglect the heat flux by radiation, we are left with this equation with the only contribution here different than a pure substance is the divergence of all the contribution to the heat flux from diffusion. Okay. There are a couple of alternative forms to write the energy equation. And I am going through this just because sometimes there appear to be a confusion between when you see the equation in one form or another in the literature, thinking of there may have been, I don't know, some simplification or what have you. But you can write the equation slightly two different forms, and I am not going to go through the detailed derivation, but just allude to it. So here is one of the form. I called it here version 1. Both of them starting from this same general form of the energy equation, which I have expressed in terms of the enthalpy. And the idea is just to introduce for the enthalpy or to relate it to the temperature, basically. So in this version, what you do, you start with this term, which is the material derivative of the enthalpy of the mixture, and you replace the enthalpy of the mixture by its definition, which is the specific enthalpy plus what we often call the sensible enthalpy, which is the one contributed from the CP. And when you substitute in here, so clearly the derivative would involve the two terms, one contribution from the yi, which is here, and the other one contribution of this integral, which is here. And then this term that is essentially rho dyi dt multiplied by the specific enthalpy I took to the right-hand side of the equation, which is here, okay? Now, the fluxes term here, similarly, the HI can be written as the specific enthalpies and the sensible enthalpies. And when you take the divergence of this and manipulate this term, clearly one of the contribution will still have those specific enthalpies, which is here, and the remaining term. Now, you see that what's here under this bracket, it's exactly the left-hand side of the species equation, and so it's equal to omega I, the rate of consumption of species I. And so the end result is that you can write the equation as d by dt of the integral of Cp dt, which is the sensible enthalpy. Those terms don't change. They are the same. That's just dp dt, the viscous dissipation, the heat conduction. And this is what was left from here, which is the energy transfer due to diffusion fluxes caused by the fact that the different species have different specific heat. I will comment on this again in 1 second. And the last term is this omega I times the enthalpies of formation, okay, Hi naught. Now, I said here that this is due to specific heat because it's clear that if all the CPI were the same, the bracket here is independent of I, and the sum of yi vi is 0, so that term is gone. Okay? So the contribution here is due to the essentially variation of the CPI. Now this form, called version 1, has in it the sum of the omega I multiplied by the specific heat of formation, right? The next version that often appears in different publications or books or whatever, has the form Hi multiplied by omega I. Omega I multiplied by Hi, not of formation. But the equation is slightly different than the previous one, and they are both correct. They are both identical, but they are of different form. And the way to come to this form is to express the enthalpy directly in terms of the temperature using the definition of one of the previous definition of the total enthalpy H, okay? And then that term will bring in, where is that now? well, anyway, through some of this manipulation, what you get is again the balance equation of species I, right? The equation for yi, which is omega I, but this time it's multiplied by hi. In other words, what we didn't do in this derivative, we didn't split hi in terms of the specific heat plus the integral. We just left it as hi. And so you end up with this relation, but that term is a little different than the previous one that we had in the previous equation. Now let me see what's in my, yeah, here are the two versions. You see that they are slightly different in form. Both in these two terms are not identical, and neither these two terms. And therefore, the sum here is not the same. Here it's multiplied by hi naught, and it's hi. Some people call this, as we shall see later, the heat of combustion, and some people call this the heat of combustion. So the question is if the heat of combustion include the sensible heat of formation or not. That's the only difference. Now, of course, if you assume that all the CPI are the same, the two equations reduce to the same equation, and it doesn't matter, right? Because if all the CPI are the same, I told you already that this drop to 0, but because the CP is common, then yi vi, the sum over all I is 0. Same thing here, yi vi sum of all I is 0. This is independent of I. And so these terms are gone. And then if Cp is independent of I, then that can be integrated to give you dt dt. And on this side, of course, it's again, the two are identical. And so when all the CPI are the same, what you have is the expression which I left here framed. Rho Cp dt dt, dp dt, the phi, the viscous dissipation, heat conduction, and what we will see later we refer to as the heat of combustion. Okay, so most of our discussion will focus on this equation because in theory, of course, it's difficult to do anything if you allow for all the CPI to be different, and so we're going to assume that. Okay, but I thought it's just important as a, I don't know, it's more than a curiosity, but just as a fact that you can see these two equations in the literature and note that they are really identical. You have to manipulate a little bit, but they are the same. Okay, diffusion. So we talked about heat conduction, and now the next thing is diffusion. I don't know how am I doing in time now. I am totally lost. We started late. Let me finish this, then we'll take a break. We may go a little over today, but I'll cut it some other time. So diffusion, I want to start quickly with Fick's law of binary diffusion. Assuming that we have only two species, then the law by Fick state that the flux, okay, rho yi vi, rho y1 v1 of species 1 is depending on the concentration, on the gradient of the mass of 1, which is gradient y1, with a coefficient which is material dependent, very similar to the law, to a Fourier law of heat conduction. Okay, very similar. Again, the negative is because it goes from high concentration to low concentration. And if I write this same statement for species 2, it's going to take that form, right? And for the time being, I left D1, 2, meaning the diffusivity of 1 into 2, and D21, the diffusivity of 2 into 1, okay? And those are the diffusivities which have units of centimeters squared per second, right? Area per time. Now, since the sum of y1 v1 plus y2 v2 must be 0 in a two-species system, then, and because y1 plus y2 is 1, meaning that the gradient of y1 is the same as minus the gradient of y2, right? Then clearly d1, 2 must be equal to d2, 1. And so in a binary diffusion in a binary system, the diffusivities of 1, 2, and 2, 1 are the same. I call them D, and this is essentially Fick's law. Okay? So Fick's law states that the flux by diffusion is proportional to the gradient of the mass fraction yi, and the coefficient is the diffusivity, which is either of 1 into 2 or 2 into 1. Okay? Now, if you substitute that into the species equation, remember we had a term here which was just the divergence of the diffusion fluxes. So we replace this rho yi vi by the appropriate term. So we are going to get now, there's a mistake here, it should be minus. So we're going to get, I told you that there are some typos. So rho d gradient of yi, okay? If rho d by luck or by choice is taken to be constant, then that becomes the Laplacian of yi, and this is the known diffusion equation. Of course, it's true only if you correct the typo. Otherwise, it's not the diffusion equation, it's not a good equation because it blows up and it doesn't diffuse as it should. Anyway, this is good for a binary mixture. What happened in a mixture that you have many species? Well, the more comprehensive multi-component diffusion law was written by Curtis and Hirschfeld, and it takes this form. First of all, it's not expressed in terms of the mass flux as we wanted in this equation, or as we have in this. It's written in terms of what is the concentration gradient caused by diffusion. Okay, so its gradient of xi is, first of all, there is a difference in diffusion velocity between two species, any two species, I and j. Then you have a contribution due to the pressure gradient. In other words, pressure gradient cause change in concentration or cause a gradient in the mass in the mass fraction or concentration fraction. And you have a contribution from the temperature. Different temperature can cause that. This is often known as the Soré effect. And also body force can cause a change in concentration.
So the pressure gradient was yi minus xi.
I'm sorry?
Why is it yi minus xi?
Yeah, yi minus xi.
Xi is the molar fraction, right?
This is mass fraction, this is mole fraction.
That makes sense. Why they
Well, that's how, in units it's okay, and I am pretty sure I typed it right. I don't remember it by heart.
I did try to understand the physical meaning about yi minus xi.
But this is not the important thing. The important thing is the grad P over P.
Yeah.
Okay, so there's, in other words, the idea is that pressure gradient cause change in, cause diffusion. And so if you were to use this, I would suggest that you verify that first, because I cannot, something that I don't use very often because I'm not, we typically neglect this because the effect of pressure gradient and even temperature gradient, which is a Soré effect, are very often neglected. But Soré effect turned out to be sometimes important, and people have discussed that on occasion. We're going to neglect that in the in these lectures. The last term arises when there are unequal forces acting on the species. For example, and I mentioned that earlier, if you have ions and electrons, which due to some electric field, there is different forces acting on them. So some of these species and the difference between them cause some difference that lead to a change in concentration. Okay. Again, we're not going to discuss those effects. So I think from now on, I will always neglect these body forces differences. Okay, so if we neglect all these, we end up with the more common expression used in combustion, which are the Stefan-Maxwell relations. And this is essentially the first term in that expression, which is the gradient of xi is xi xj divided by dij. Those are the diffusivities of species ij. In other words, the diffusivity of I into j. And then the diffusion velocity Vj minus Vi. For a dilute ideal gas mixtures, they are basically, these Dij are independent of concentration. They can be determined by a simple two-component experiment where one species, let's say I, is put in small amounts into a big amount of J, and the diffusivity can be measured, the Dij can be measured in this way. So in other words, what I wanted to express here is essentially that they are fundamental, those diffusivities. I'm going to run quickly through just the diffusion part, and then I'll take a break. The first comment I want to make is that in a binary mixture, if you take the Stefan-Maxwell relation and just replace the n with 2, so j go from 1 to 2, then clearly you can write what grad of x1 is and grad of x2 is, which is written here. And if you add them up and you use the fact that x1 plus x2 is equal to 1, so the gradient of the sum is 0, and on the left-hand side you're going to have just the difference between these two. Since the left-hand side is 0, as I just indicated, then clearly d12 must be equal to d21. And as a consequence, you also obtain the manipulation here takes some algebra, but can be done easily, and you can show that you get Fick's law. So the Stefan-Maxwell, the key point in that slide is to tell you that the Stefan-Maxwell relation lead to Fick's law if you have two species. Well, what if you have many more species? Well, it's too complicated. So some people have chosen to use something which is called the generalized Fick equation. In other words, what you write is that the diffusion velocity Vi, it's a sum of Dij gradient of xj. I used here a different D on purpose because these are not the diffusivities which you measure, as I said earlier, which are more fundamental, okay? And in fact, if you take even a simple example of a binary mixture, you find that these coefficients are not constant. They are concentration dependent, unlike the diffusivities, which are fundamental, and they should be properties of just the two species. So this is one complication of using that Fick's generalization. The other thing, and here is, by the way, what the expression will look for ternary mixture. You can find that in, it's taken from Bird, Curtis and Bird, but it's also appeared in one of those books. Chemical engineers use those a lot, so you can find that there. But anyway, the point is that this were expressed in terms of the xj, right? And what we would like in the conservation equation that we derived to express that in terms of the yj, the mass fraction. So it's not going to be the same di, it's going to be some di hat. And the relation is such that the gradient of xi and the gradient of y, the different y's, is not simply correlated. It's more involved. It takes, it depends on the molecular weights and the change in the molecular weights and so on. So you can get quite complicated expression for this Dij, and so it's not, it was just few comments about this generalized Fick's, the generalized Ficksian, what I call the generalized Fick equation. Okay, but we want to try to simplify somehow this Stefan-Maxwell relation, certainly for theoretical consideration, and there are two ways that are usually done. One of them is if you assume that the mixture is dilute. So for example, if you are burning some hydrocarbon in air, there's a lot of nitrogen, and so you can assume that nitrogen is an abundant species, and so everything is diffusing in principle into nitrogen. So you can follow the Stefan-Maxwell relation, assuming that all the species except of nitrogen, which you call N, species N, are small in quantities, and therefore the mass fraction is small, the mole fraction is small, and the diffusion velocities of N will be small, but all the others will be important. And so when you substitute that in the Stefan-Maxwell relation, you essentially obtain Fick's law for each species, but the coefficient here is this one, is DIN. In other words, it's the diffusivity of species I into the abundant. It makes sense, but it also follows systematically from the Stefan-Maxwell relation. So if we are going to use a dilute mixture, the understanding is that if we are going to use Fick's law for a dilute mixture, the understanding is that the diffusivity is the diffusivity of species I into the bulk, into the abundant mixture, the abundant species in the mixture. Well, you can do this for N-1 species, now all the ones which are scarce. What about the N species itself, the nitrogen, say, right? Well, for the nitrogen, it's not true that you can write a Fick's law. In fact, the right-hand side will be very messy, will contain all many terms. But luckily, you don't need it because you can compute it from the fact that the sum of all yi is 1. So if you're assuming Fick's law in your species equation, never use all the N equation, because if you do that, you're not satisfying mass. You're not conserving mass. You have to only use N-1 relation with the N species obtained from this relation. I'll probably emphasize that comment. I'll make that comment again later. Another way to use an approximation is the so-called effective diffusivity. What you assume there is that only the diffusion of species I is in the mixture, but all the other Vj are approximately 0, are very small. And if you do that, you can obtain an effective diffusivity, which is written here in terms of mole fraction. And again, you can use this only for N-1 species because it's not exact. So if you use it for all the N species, you're again not conserving mass. So the last species must be obtained from one of the, for example, the diffusivity of the last one should be obtained from this constraint. Let me see what we have here. Okay, so I think this is the last one or two last ones. So let me do that, and then we'll take a break. But okay, so what we now have, if we in the future or in these lectures, I'm going to assume the mixture is dilute. So I'm going to assume Fick's law taking this form, right? And the di, as I said, I'm going to just use the I without an n for simplicity. But the meaning is it's din, which means the specific, the diffusivity of species I into the inert or into the abundant n. And if you substitute that in the species equation, then you get essentially a similar equation or diffusion type equation for all the species, of course, with the omega I on the right-hand side. We can only use those for N-1 species, and the last one obtained from yn equal to the sum of all yi, 1 minus the sum of the remaining yi, right? And we can only use those for those which are scarce, which are limited in the mixture. All right. What we have accomplished, and I think this is my last slide in this set, is we have mass conservation of the total mixture. We have the momentum equation, so we have the Navier-Stokes equation. species equation here, which are written for species I, the energy equation written in terms of the temperature in the form that I chose to write, namely with the HI naught here, the enthalpy of formation, and the ideal gas law, and that to close the system, we have enough equation with enough unknowns. We can count them again, but I did that exercise before, so it's about the same as before. The only thing which we have to speak about briefly is the transport coefficient, which is the viscosity, bulk viscosity, diffusivity, and conductivity. And I'll talk about that after the break. Let's take a short break, if you don't mind, so that I can at least finish part of next lecture today.